So our next topic is circulation and vorticity. Now what is circulation? How can we define circulation? The circulation around a curve is defined as the summation of product of velocity component along the element of the curve and the elemental length ds. Product of summation of product of velocity component along the element of the curve and the elemental length ds, and it is denoted by this letter Greek uppercase of gamma. Okay, now what is the circulation? So suppose we are having a closed curve like this, suppose. Okay, now we want to determine the circulation around this closed curve. So we are considering a small element ds here. A small element ds is considered such that now if at this element, if I want to determine the velocity at these 2 points, the velocity here will be perpendicular to this curve and velocity at this point will be perpendicular to this, like this. Getting this? And let's suppose the angle between the two is suppose theta. Okay, now the product of summation of velocity component along the element of the curve. So suppose this velocity is v, so along the element of the curve, this is small element, this angle as I told you is theta. Okay, so this the velocity along the element of the curve is v cos theta into the distance of the curve is ds. Okay, so if I take the summation of this. Okay, so how can we understand this circulation? So suppose we are having a closed curve like this, okay, and we are considering a small element in this closed curve. A small element of length ds is considered. Okay, if I want to determine the velocity here, the velocity vector here will be perpendicular to this. Okay, and suppose this angle is theta. Okay, now how have we defined the circulation? Circulation is defined as the product of summation of velocity component along the element of the curve. Velocity component along the element of the curve. Okay, so the velocity component along this ds is nothing but v cos theta. Okay, and the product of this v cos theta and the elemental length ds. Okay, if I take the summation, if I integrate it over whole curve, I will get what? Circulation. Okay, so this is how we can define circulation. This is how we can find this circulation. The product of the summation of product of velocity component along the element of the curve and the elemental length ds. Okay, so this is known as the circulation. Now I will make this more clear. Let's suppose we are considering a rectangular element. Okay, now let's suppose we have this rectangular element of distance, suppose dx dy, the dimensions are dx and dy. Okay, this is a b c d. Okay, now suppose the velocity here is u, the here velocity suppose is varying with respect to y direction, and here the velocity is u plus del u by del y into dy. Getting this? U is varying with respect to y axis. Similarly, v is the velocity in y direction and this is varying with respect to x axis. So here the velocity will be v plus del v by del x into dx. Getting this? Okay, so the small circulation d gamma is equal to, okay, so what is the circulation? This is nothing but the summation of product of velocity component along the element of the curve and the distance of that component. Okay, so over this whole curve, over this whole cycle, if I want to determine the circulation, so what will be the circulation now? So just understand this thing very carefully. So at this point, at this AB elemental length, the elemental length is dx and the velocity component is here is u, so this will be u into dx. Getting this? Plus for this BC, elemental length is dy and velocity component is v plus del v by del x into dx. So this will be plus v plus del v by del x into dx into dy. Getting this? Now for here, for CD, now if we are considering anti-clockwise as positive, so clockwise will be considered as negative. Okay, so for this CD, this will be minus u plus del u by del y into dy into elemental length, which is dx. Getting this? For AD minus v into dy. okay, u into dx plus v plus del v by del x into dx into dy minus u plus del u by del y into dy into dx minus v into dy. I think this is clear. Okay, so this d circulation, this will be equal to what? If I solve this u dx and u dx will get cancelled out, v dy and v dy will get cancelled out, and we will get what? So this will be del v by del x into dx dy minus del u by del y into dx dy. Getting this? Okay, now further this can be written as d circulation will be equal to del v by del x minus del u by del y into dx into dy. Okay, where this d gamma is equal to differential circulation around the rectangular element of enclosed area dx dy. Okay, so this is how we can determine this circulation around the closed curve. Okay, this is for the rectangular element. Getting this now? Okay, next is the vorticity. Now what is vorticity? Vorticity in simple terms, if I define, vorticity is the circulation per unit area enclosed by the curve. The circulation per unit area enclosed by the curve, or you can say it is the ratio of differential circulation around an infinitesimal closed curve enclosing the point to the area of the closed curve. That means you just have to take the ratio of circulation to area. Okay, so we will discuss the same case as I told you about this rectangular element. Here the circulation was del v by del x minus du dy into dx dy, and area here is dx into dy. Okay, so if I want to determine the vorticity, so here vorticity zeta, this is denoted by zeta about z axis, is equal to d circulation divided by dx into dy. Okay, now here as I told you, this d circulation is what? So this d circulation here is del v by del x minus del u by del y into dx dy divided by dx dy. Okay, so this gets cancelled out, and we will get what? This will be equal to del v by del x minus del u by del y. Okay, so this is called as the vorticity, and this vorticity is actually a vector quantity. And if I tell you the direction of this vorticity, the direction of the vorticity is the perpendicular to the direction about which we are taking this vorticity. That means perpendicular to this plane. Okay, so this perpendicular to the plane, that means this direction. Okay, this will be the direction perpendicular to this paper. This will be the direction of this vorticity. Getting this or not? Okay. Now vorticity vector, how can we define this vorticity vector? Okay, this can be defined as this I cap, j cap, k cap, del by del x, del by del y, del by del z, u, v, w. And this is very simple method to remember this vorticity, because where we have to put v, where we have to put x, where is u, where is y. So don't get confused. I will tell you, this is very simple thing to remember. Okay, so from here we can determine this vorticity vector. So this vorticity vector will be equal to, this will be I cap into del w by del y minus del v by del z, this into this minus this into this. Getting this? Okay, plus j cap, when I am taking this, so this will be del u by del z minus del w by del x, del u by del z minus del w by del x. Okay, plus k cap. Okay, so this will be del v by del x minus del u by del y. Getting this? Okay, so vorticity vectors, as I told you, zeta z is equal to what? Del v by del x minus del u by del y. Similarly, if you want to calculate zeta y, okay, so this zeta y, this will be equal to del u by del z minus del w by del x, and similarly zeta x will be equal to del w by del y minus del v by del z. So okay, so this is how you can easily remember this. You will not be confused with this. Getting this? Okay, now I told you about the rectangular element. Now what about circular element? What will be the circulation and what will be the vorticity for a circular element? Suppose we are having a circular element of radius, suppose r, okay, and we are considering a small element, the angle between them is d theta. Okay, so here this velocity will be is equal to what? Omega into r. Okay, and the circulation around this circular boundary will be equal to integration of the product of the summation of product of velocity along the curve and the distance of this curve. Okay, so this will be equal to what? V into the distance of this curve is nothing but r into d theta. Arc is equal to angle into radius, so this distance arc is equal to r into d theta. Okay, so this d circulation is equal to integration of v r d theta. Now v can be further written as omega into r, as we know, so this will be equal to what? Integration of omega r square into d theta. Okay, so from here this d circulation will be equal to omega r square into what will be the integration of this d theta? D theta is a small angle. If I integrate it over the whole curve, I will get what? 360 degree, or you can say 2 pi. So this will be omega r square into 2 pi. Okay, this is the circulation around the circular path. Okay, now similarly we can get the vorticity at a point. So the vorticity at a point will be is zeta will be equal to d circulation divided by area of this curve. So this will be equal to what is d circulation? Omega r square into 2 pi divided by area of the circle, which is pi r square. Okay, so this will be equal to what? This pi will get cancelled out. Okay, r square will get cancelled out, and this will be equal to 2 into omega, or you can say 2 into omega z. Okay, that means you can say the vorticity is equal to 2 into rotation component about z axis. This omega is nothing but rotation about z axis. Okay, this is the rotating about z axis. So this vorticity is equal to 2 into rotation component about z axis. Getting this now? Okay, I will tell you with an example. This was asked in GATE 2007. A question was asked in GATE 2007. How can you determine the vorticity? So here the velocity vector is given as 2xi plus yj. Okay, and you have to calculate vorticity at point 11. Okay, now how can we calculate this? So as I told you, vorticity is equal to what? Del v by del x is equal to del v by del x minus del u by del y. Okay, now what are the components here? So here u is given as 2x and v is given as y. Okay, so del v by del x. Now this v is equal to y, so del v by del x will be equal to 0. Similarly, del u by del y, u is equal to 2x, no y here, so del u by del y is also equal to 0. That means the vorticity is 0 for this particular case. Okay, very simple to determine. Okay, so this is how we can determine the vorticity. Okay, next is the irrotational and rotational flow. Okay, now what is an irrotational flow and what is a rotational flow? Now irrotational flow is defined as the flow in which the net rotation of the fluid element about its own mass center is 0 as it moves from one place to other. Okay, net rotation of a fluid element about its own mass center is 0 as it moves from one place to other. Net rotation about its own mass center is 0. That means suppose we are having a fluid element like this. Okay, and this is rotating in any curved path, but the net rotation of this fluid element about its own mass center is 0, then we can say that the flow is irrotational flow. Okay, this element is not rotating about its own mass center, so this is an irrotational flow. On the other hand, if I tell you about the rotational flow, in rotational flow this will rotate about its own mass center like this. Suppose initially the element is like this. Okay, so this will, after some time it will be like this, then it will be like this. Getting this now? That means this element is also rotating about its own mass center. This element, however, is moving in the curved path. Okay, so it doesn't matter whether it is moving in a curved path or a straight path. But if the element is not moving, rotating about its own mass center, then we can say that the flow is irrotational. And if the element is moving about its own mass center, then we can say that the flow is rotational. And for this irrotational flow, the vorticity must be always 0. Very important thing. For an irrotational flow, the vorticity must be 0. Okay, similarly, as I told you, the rotational flow, what is a rotational flow? In which the vorticity is not 0. Okay, or the element is rotating about its own mass center. Okay, so you can define rotational flow from here. In such flow zones where vorticity is non-zero, the flow is said to be rotational. Getting this or not? Okay, now, so now let me elaborate a little about this irrotational and rotational flow. So basically there are 4 types of displacement in any type of motion. So the 4 types of displacements. Whenever some body moves, whether it be solid or whether it be liquid, they basically follow 4 types of displacement. The very first displacement is the linear translation, or you can call it as pure translation. Linear translation or pure translation. Second is the linear deformation. Okay. Third is angular deformation. And last one is the rotation. Okay, so these are 4 types of displacement if any body is moving. Okay, now let me explain you this. Now what is this linear translation? So this linear translation you can understand like this. Suppose we are having an element of dimensions, suppose dx and dy. Okay, now in this linear translation, this u is always constant, u is constant, and v is also constant. That means u is not changing with respect to space coordinate and v is not changing with respect to space coordinate. Okay, let me explain you this thing. U is constant. What does this mean? That means in this particle, this u is not varying with respect to x-axis, neither this u is varying with respect to y-axis. That means u जो है वो पूरे particle में same है. x-axis का जो velocity है, that is same in each and every particle at each and every point of this particle. That means अगर ये इस point की velocity, if this point is having a velocity u, this point is also having velocity u, this point is also having velocity u, this point is also having velocity u in x-axis. Okay, similarly v is also constant. That means if this point is having velocity v in y-axis, this point is also having velocity v, this is also having velocity v, and this is also having velocity v in y-axis. All the points are having the same velocity in x and y-axis. Now what does this mean? This means that the whole particle will be parallelly shifted. Parallelly shifted, that means after some time this particle will be at this point. Okay, and this distance, obviously suppose after time dt, okay, so this distance is nothing but u into dt. Okay, this will travel by a distance dt, so this distance is nothing but u into dt. Similarly, this distance is nothing but v into dt. Okay, so this is how linear translation occurs. Linear translation means at each and every point the x component of velocity and y component of velocities are same. Getting this thing or not? That means there will be no deformation here because all the points are having the same velocity. They are moving with the same velocity. There is no relative velocity, so there will be no deformation here. There will be just a displacement. There will be just a translation. Getting this? Okay. Okay. Next is the linear deformation. Okay. Now, what is linear deformation? How can you understand this linear deformation? So suppose we are having an element, same element we are considering, of dimensions dx and dy. Okay, now here in this particular case, del u by del y is equal to 0, del u by del y is equal to 0, and del v by del x is equal to 0. That means u is not changing with respect to y coordinate. Okay, u is changing with respect to x coordinate. That means del u by del x is not equal to 0, but u is not changing with respect to y coordinate. Now what does this mean? This means, suppose if at these are 4 points a, b, c, d. Suppose point a, b, c and d. Okay, if at this particular point we are having the velocity u. Okay, so this is not changing with respect to y-axis. So in all the points of this AD, the velocity in x direction will be same as that of u. Getting this now? Okay. Now, but velocity is changing with respect to x-axis. That means here velocity is u. Now at point B, the velocity is changing. So here the velocity will be u plus del u by del x into dx. Okay. The change rate is del u by del x into the total distance, which is dx. So u plus del u by del x into dx. This is the velocity at point B. Getting this now? Okay, now similarly getting into this, del v by del x is not equal to 0. That means the velocity here is v at point A. The velocity in y-axis is v. Okay, and this is not changing with respect to x-axis. That means at all the points of AB, velocity will be same as that of v. Here also velocity will be v. But this velocity v is changing with respect to y-axis. Del v by del y is not equal to 0. This del v by del y is not equal to 0. That means here velocity will be more, and here the velocity will be v plus del v by del y into dy. Getting this? Here velocity is u and y-axis velocity is v. Here velocity is u plus del u by del x into dx. Okay, and at this particular point, at point D, v plus del v by del y into dy. Okay, now what will be the final position now? Now because these 2 points, point A and point B, are having different velocities, that means this after time dt, this point A will move by a distance, suppose u into dt. But at the same time, this point B will move by a distance of u plus del u by del x into dx into dt. That means distance traveled by this point B is more than that of A. That means there will be a relative displacement. Getting this not? That means the final position will be like this. This was the initial position, and because this point is moving more with respect to this point, so the final position will be like this. Getting this? Similarly in y direction, here the velocity is v, here the velocity is v plus del v by del y into v dy. So this final component would be like this. Getting this now? Okay, that means this distance, the distance which u has traveled, suppose after time 1 second, this distance will be u. This is suppose a dash, b dash, c dash and d dash. This is b double dash, c double dash and d double dash. Okay, so this distance between a and a dash is u. After time 1 second we are considering, and the distance between b and b dash, this is u plus del u by del x into dx after time 1 second. Getting this now? Okay, this means what is this distance b dash b double dash? So this distance will be this minus this, so this will be equal to this will be equal to del u by del x into dx. This is b dash b double dash. Getting this now? Similarly, this distance d dash d double dash, this is nothing but del v by del y into dy. Okay, so this is how this will be deformed. Okay, because the velocities are different in different time, but still one more thing, that u is not changing with respect to y and v is not changing with respect to x. That means this element will shift parallelly. This element will still shift parallelly, because the component of velocity of u is 0 in y direction and component of velocity of v is 0 in x direction. Getting this now? So this is the case of linear deformation. If you want, you can determine the strain rate. So strain rate in x direction, sigma epsilon x, this will be equal to the total change in length is del u by del x into dx divided by the original distance, which is dx. So this dx will get cancelled out. This will be del u by del x. Okay. Now epsilon y will be equal to del v by, sorry, this is del u by del x, this will be del v by del y. Similarly, strain in z direction will be del w by del z if the same element is considered in 3D form. Getting this now? Next is the case for angular deformation, or you can call it as distortion. Okay, now what will happen in this case? And in this case is in fact the most general case which is seen in the liquid, because the first case which we have seen of the linear translation, that happens only in solid, that cannot happen in liquid because there u and v both are constant. The second case which we have seen is also very unlikely in liquid, because in liquid the velocity changes in y direction also. If the fluid is transmitted in x direction, as we have seen, the velocity also changes in y direction because of the friction. Okay, so this case is in fact the most general case in case of fluid, when this del u by del y is not equal to 0 and del v by del x is not equal to 0. That means the velocity u will change with respect to y axis also, and velocity v will change with respect to x axis also. I will show you how. Okay, so considering the same element of dimension dx dy, okay, now here at this particular point, at point suppose A, the velocity here is u in direction x, the velocity is u. Okay, now this u is changing with respect to y axis. Okay, del u by del y is not equal to 0. What does this mean? That means this u is changing with respect to y axis. That means the velocity at this point is far more, which is equal to u plus del u by del y, sorry, into dy. U plus del u by del y into dy. Getting this now? Okay, similarly the velocity in y direction at this point is suppose v, and this del v by del x is not equal to 0. That means v is changing in this direction, and finally at point B the velocity will be v plus del v by del x into dx. Okay, I think this is clear. Okay, and I think the difference is clear from the previous case. What happened in the previous case, this del u by del y was equal to 0 and del v by del x was equal to 0. That means this u was not changing with respect to y axis, and v is not changing with respect to x axis. That means here the velocity at both the points was same. Here we have different case. That means here the velocity is u, but this is changing with respect to y axis, so here the velocity will be u plus del u by del y into dy. Getting this case or not? Okay, now what will happen? So because here the velocity is v and here the velocity is v plus del v by del x into dx. Okay, so the final element, if I draw, so the final element would be like this. Okay, now because there is a relative velocity in this direction, here velocity is less, here velocity is more, so this element will distort like this. Getting this? Again here velocity is less, u, here velocity is more, so the final position will be like this. Getting this one? Okay, now so let's suppose this angle is d alpha and this angle is suppose d beta. Okay, now what will be this distance? This distance. What will be this distance? Distance is equal to the velocity into time. Okay, so after time suppose dt, the net velocity in this direction is del v by del x into dx into dt. Getting this? Because after time dt, the element will be somewhat here. This a point will shift at suppose point at suppose this point. This distance will be u and this distance will be v. Okay, and from here now we are measuring this. So from here we will be having the element like this. I'm just drawing the rough element. Okay, like this. Okay, so this distance, which is equal to speed, velocity into time, del v by del x into dx into dt. Similarly this distance, so this distance will be equal to again del u by del y into dy into dt. Getting this? That means this OA is shifting in anti-clockwise direction and this AD is shifting in clockwise direction. Okay, now we know what now because there is a shift in the angle is changing. Okay, so the angular velocity omega, let's suppose this is A, B, C and D. Okay, so the omega AB will be equal to d alpha by dt, rate of change of angle d alpha by dt. Okay, now what is d alpha? So because this angle is very small, so this d alpha can be nearly equal to tan of d alpha. So this d alpha, which is nearly equal to tan of d alpha, and tan of d alpha is what? Perpendicular upon base. Okay, this distance is dx. Okay, so here we have del v by del x into dx into dt divided by dx. So dx get cancelled out and we will get what? So this will be equal to del v by del x into dt. Okay, this is d alpha. Getting this now? Okay, similarly d beta we can determine. Okay, so what will be d beta here? So this tan of d beta, which is nearly equal to d beta, which is equal to del u by del y into dt. dy and dy will get cancelled out. Clear or not? Okay, now